Hello everyone, welcome and thank you for listening to my presentation. I am Ahmed Nasr Batrawi, presenting our work on secrecy performance of joint antenna and user selection in cognitive ambient backscattering communications. This paper is submitted to VTC Fall 2024, and this work is under supervision of Associate Professor Ahmed Abdelmalik, Professor Sharif Rabia, and Professor Wahid Zahar. The outline of our presentation: we start with an introduction explaining the background, the related work, and the motivation and contributions of our work. Then we explain the considered system model. After that, we investigate the secrecy outage probability analysis. Then we present some numerical results and end with conclusion and the future work. Massive deployment of IoT devices has become essential in different applications, such as agriculture, logistics, smart cities and buildings, monitoring and control in industrial applications. However, this massive deployment has different challenges, such as spectrum scarcity, limited energy resources, and security. Therefore, different wireless technologies have appeared to tackle these challenges, such as ambient backscattering communication, where the backscattering device modulates its data on the signals of an ambient RF source. Hence, it doesn't need a dedicated spectrum and saves the energy needed for generating carrier signals. Moreover, incorporating cognitive radio network with ambient backscattering communication achieves better spectrum utilization. From a security perspective, the massively deployed IoT devices have low computational capabilities. Therefore, they can't apply complex cryptography techniques to ensure security. Physical layer security provides a complementary, promising approach to secure the transmission by exploiting the random nature of wireless channels. Therefore, in our work, we are interested in secrecy performance of ambient backscattering communication cognitive radio networks, which has been considered in literature in references 5, 6, and 7. However, in all the previous work, they have considered intercept probability as a security metric over really fading channels, considering a single antenna nodes with single receiver user and single eavesdropper. Different from the previous work, we consider secrecy outage probability as a security metric over Nakagami M fading channels, which generalizes the previous assumption of relay fading. And we consider a network with multiple receiver users and multiple eavesdroppers, where the secondary transmitter is equipped with multiple antennas and perform joint antenna and user selection. Our contribution can be summarized as follows: investigating the secrecy performance of an ambient backscatter communication cognitive radio network with multiple secondary receivers and multiple passive eavesdroppers over Nakagami M fading channels, where the secondary transmitter is equipped with multiple antennas and perform joint antenna user selection as a physical layer security technique. Closed form expressions for secrecy outage probability for both the secondary transmitter and the backscattering device transmissions are derived, and their accuracy is verified using Monte Carlo simulations, and we study the effect of different system parameters on the system performance. Our considered system model consists of a single secondary transmitter equipped with multiple antennas and multiple receiver users, a backscattering device, and a primary user that owns the spectrum and constrains the secondary transmitter power. Multiple eavesdroppers tries to overhear the transmission of both the secondary transmitter and the backscattering device. We consider Nakagami M fading model, and hence the channel power gains are gamma distributed with the given BDF and CDF. We also employ joint antenna and user selection based on the channels between the secondary transmitter antennas and the receiver users. We select the antenna user pair that has the best channel conditions. For secrecy outage probability analysis, we consider SOP analysis for both the secondary transmitter and the backscattering device. For the secondary transmitter, we consider the effect of the eavesdropper that has the best channel to the selected antenna, and we compute the secrecy capacity of the corresponding channel. And for the selected antenna user pair, the secrecy outage occurs when the secrecy capacity is less than a given target rate. And in terms of network parameter, this can be expressed as follows, where the CDFs of this random variable is given here. And we consider an interference limited scenario where the noise power is negligible. With some mathematical manipulations, we can get to this closed form expression for secondary transmitter secrecy outage probability, where this is generalized by varied measure G function. And we can notice here that in the interference limited scenario, the secondary transmitter secrecy outage probability isn't affected by the primary user interference threshold or the secondary transmitter transmission power. For the backscattering device secrecy outage probability, we consider the effect of the eavesdroppers that has the best channel to the backscattering device and compute the secrecy capacity of the corresponding channel. And the secrecy outage occurs when the secrecy capacity is less than a given target rate. Using total probability, it can be computed as follows, and it can be re-expressed in terms of network parameters. And we are sorry for a typo here. It's a plus sign, not a product sign. And with some mathematical manipulations, we get to the final closed form expression. For numerical results, we consider the effect of different system parameters on the secrecy outage probability of both the secondary transmitter and the backscattering device. Firstly, we consider the effect of the quality of the channel between the backscattering device and the users. As the mini channel power gain increases, indicating better channel quality, the secondary transmitter secrecy outage probability increases, which indicates a lower security performance due to the increasing effect of backscattering device interference, while the backscattering device secrecy outage probability decreases due to the high signal-to-noise ratio received at the users. For the channels between the antenna and users, increasing the Nakagami M parameter indicates lower fading and better channel quality, leading to a better performance for the secondary transmitter due to the higher signal-to-noise ratio received by the users. Increasing the number of users and antennas decreases the secondary transmitter secrecy outage probability, which enhances the security performance of the secondary transmitter. This is due to exploiting the antenna and user diversity, while not affecting the backscattering device secrecy outage probability, because the selection doesn't consider the channels to the backscattering device. Increasing the number of eavesdroppers, increasing the secrecy outage probability for both the secondary transmitter and the backscattering device due to the diversity of eavesdroppers. And finally, for the channels between the backscattering device and eavesdroppers, increasing the quality of these channels enhances the secondary transmitter performance because the secrecy outage probability decreases. This is due to the increasing backscattering device interference on the eavesdropper, while the backscattering device secrecy outage probability increases due to the higher SNR received for the backscattering device data at the eavesdroppers. Finally, we can conclude that in the interference limited scenario, the secondary transmitter secrecy outage probability isn't affected by the primary user interference threshold and the secondary transmitter transmission power. Under the adopted selection scheme, the backscattering device secrecy outage probability isn't affected by increasing the number of the secondary transmitter antennas or the number of users because the selection criteria doesn't consider the backscattering device channels. There is a reverse relation between the secondary transmitter and backscattering device secrecy outage probabilities due to the effect of the backscattering device interference. Using joint antenna user selection can elevate the effect of backscattering device interference and enhances the secondary transmitter secrecy outage probability. As a future work, we can consider the active eavesdropper scenario and use other physical layer security techniques such as artificial noise or cooperative jamming combined with different selection criteria. Thank you.